Hello everyone, so I'm Carole Sudre, and in this week lecture of Advanced Machine Learning, we'll mostly focus on a solution for object detection. So the objectives of the lectures are the following. So first, understanding obviously why we need object detection, what it is, and getting a bit more insight of what are the different existing object detection techniques, understand the different steps, and how we can further combine object detection with segmentation when needed. So in your tutorial or in your notebook this week, we'll focus on one specific type of network, which is a two-stage detector network. We'll see that step by step. And you should be able, at the end of the lecture, to implement an anchor system for what we call region proposal network. We'll see that later on. Trying also to understand better the difference between anchor-based and anchor-free system and what are their respective advantages and limitations. And we'll also see the distinction between one-stage and two-stage detector system. So let's try with some definition and trying to see what's the distinction that we can do between segmentation, object recognition, and object detection. So segmentation is usually when you have to classify each individual pixel of an image, and there is, by definition, with that task, no immediate link between a voxel and its neighbors. Obviously, that can be enforced when you perform the segmentation, but by definition, I take every single pixel and I give and I assign a class to it. And so from segmentation, you can get information about the overall volume, information on the shape, on the border, and so on. Typically, you see that when you have, for instance, brain segmentation or pathology segmentation, and so on. What object recognition is actually trying to define an entity. So it's considering an object as a whole in the context of an image, and it's saying, well, I identify in this image a specific object. So for instance, you could have that in when you are classifying frames of videos for surgery, where you indicate if a specific tool is present or absent in that specific frame. Now, object definition localization. So when we try to define an object, usually we need to know what it is and to know where it is. And so one classical way of defining the localization is to define the box that surrounds it. And classically, people are mostly using axis-oriented boxes, meaning that you follow the x and the y axis for the border of the box. And you need for that a landmark location, for instance, the corner bottom left of your box, and the box extent. And for the classification, it's the chosen class that you would assign to the object. So is it background? If it's a lesion, is it a malignant lesion or is it a benign lesion? Type of thing. So here you have typical example in image of what segmentation versus object recognition versus object detection is. So you have on the left hand side you see, for instance, classification task where there is a cat in this image, but you don't know where the cat is. When you combine classification and localization, then you know that there is a cat and you have a bounding box around the cat. When you consider object detection, is like here you have these different classes, so cat, dog, and duck. Cat, dog, and duck, sorry. And you see which for each of them specific bounding boxes that may be overlapping, but that correspond each time to a different object. And finally, with instance segmentation, so it's one step further here where you have for each of these objects the segmentation associated to it. And you have similar example on the right hand side. So how do we define object properly in terms of location, localization, and class? So here all the examples are given in 2D, but it's relatively straightforward to modify them to 3D. The bounding box can be one corner plus the width and the height. It can be based on the center, where you know afterwards the distance to the border. For instance, the distance to the top border and the left border. It could be also the difference to the bottom border and the right border. I mean, you define it as you like. Or with the two extreme corners. It could be bottom right, top left, or bottom left, top right, for instance. And for the class, you may have multiple ways of classifying. It may be just binary, object versus not object, if you have only a single class to look into in your image. It could be multi-classes, so you have, like we had before with the multiple animals, multiple classes, and you have then to choose one among the many classes. Or there are some of other classifications that are based on hierarchy. For instance, you could imagine that you have a tree starting at dog, and then from the different dogs, you may choose a specific class of dog among those, and similarly among the cats. So here you have just an illustration of what that object definition in terms of localization is. So you would have here the target, that would be the probability that it belongs to a specific class. This is here the class car, and then you would have the center. It's a center box analysis here. So you would have bx and by that are the center of the box, then bw and bh that would be the width, the height of the box, and finally C is the final class, which is here a car. So when you consider all that in terms of computer vision, mostly 2D usually, you have often objects that are relatively big with respect to the size of the image. And the challenges that I may mention here may be very similar for computer vision problems and medical imaging problems. Usually you don't know how many of the objects are presented in each class. What you may have as well is that you may have a strong variability in the shape and the size of the different objects. It's especially true when you think of different type of lesions or different type of tumor, for instance. You may have also some overlapping objects at different scales. So we saw earlier the duck that was overlapping over the dog. You can have very similar things in medical imaging, obviously. And you may as well have a need for multiple examples, multiple scales, multiple ratios, multiple classes. So you need always to consider all the different challenges that you may have with respect to your application. In terms of medical imaging application, you can think of object detection, localization in the context of mammograms. For instance, with detection and malignancy classification of masses in mammograms. You have typically the same type of problems requiring object detection when you think of small vessel disease markers in neuroimaging, where actually the number and location of the different lesions may be of interest as biomarker. And another example, it's not an exhaustive list, but For instance, you may look into histopathology slices and look for the detection and the classification of specific cancerous cells. So now we will try to, after this introduction, try to go a bit more in depth into the different types of object detection frameworks that exist. We'll talk first about the two stages ones that actually we will focus on during the tutorial, and then we will have another part that will mostly focus on all the one-stage ones that we're gaining from all the improvement in computational power. So the two-stage detectors are actually a very natural evolution of the slow integration of convolutional networks in the computer vision world. And it consists in usually two steps. First, trying to propose location of objects, where you are trying to find all the possible objects in your image. And second, a refinement of the selected proposals, where not only do you refine your proposal, but you prune them to only select the best ones, and you further classify if it's needed. So the advantage of the two-stage one is that it's usually very accurate. If you have a good first step of proposal, it has a good recall and a good precision, but it's relatively complex to train and it's slightly longer at inference usually. In comparison, one-stage network, they directly try to refine and detect the good boxes. So the main issue there is that you may have a very strong negative to positive imbalance, where you have much more negative than positive samples. But that's a type of implementation that is really gaining a lot of momentum in the field, because there's been quite a lot of work on dealing with imbalance. It's usually much easier to implement, it's much faster at inference, but until 2019 it was actually showing lower accuracy than the two stages one. So it then depends on what you really want, either speed or accuracy. So we let this slide play quite at length, but that's the very classical strategy of trying to find objects in an image. So here you see a box that is sliding slowly across the image. And what's happening here, typically, is that at each instant of where the box changes, CNN is applied as a feature extractor just over that box, and that classify it as object or not object. And in order to assess what's happening and consider different scale, you see that you can consider multiple type of windows, where here you slide different sizes of windows to detect if there is an object at a certain scale or another. So either you actually change the resolution of the image, or you change the resolution of the box. It corresponds to the same in the end. The process is, however, extremely slow, and it's very dependent of the parameters. So if you don't choose properly the box size or the resolution size or the step between the boxes, you may really miss what's happening. And what further is that it becomes quite difficult when you have non-square boxes, because here it's only square boxes. In order to avoid the sliding windows problems that we just saw, the next step was actually to go to region proposals. And this one is the very first attempt to do region proposal for object detection, in which actually it consists in selecting patches of interest instead of making an exhaustive loop of all the possible regions that may exist in the image. And for that, they propose an objectiveness selective search, in which first they over-segment images based on regional similarities. So you can consider it as a superpixel segmentation. They then create boxes corresponding to each of the patches, and they iterate then between aggregating closely related patches and creating again boxes associated to it. And it's what you see in the project progression here from the start of the over segmentation until finally we get some specific object and specific proposal boxes. So once you have region proposals, what do you do? What does it mean? So you may actually decide to extract features from each of the proposed region because you want to know if indeed the region that you are proposing correspond to an object or not. And then you want to be able to classify it as a specific category that you want to detect. So you saw that in the biomedical machine learning course, but you have obviously many ways of proposing features. That may be texture features, you saw daisy, sift, Harlick features, but obviously you can also get features through convolutional neural networks. Then you need to classify the region as, like, is it something? Is it not something? Is it a dog or is it a cat? So you can use classical classification algorithms such as support vector machine or random forest, but again, you can decide to use CNN for it. You need also to refine the bounding box that you have because the proposals that you may first find may need to be adjusted slightly. You can do that with linear regression, you can do a bounding box based on a point grid, or you can again apply a small CNN network to it. And beyond the box, once you have properly detected localized classifier object, you may want to do instance segmentation of each object, meaning that you need to classify each pixel within that box as belonging to the object or not. And that's the mask segmentation that can be, for instance, done through mask RCNN, which is a typical object detection framework. And so in the tables that you have here, you have the evolution of the network from the first RCNN network to the faster RCNN that we will focus on implementing during this week. So with the RCNN, you have the region proposals through the selective search. Then you do your feature extraction via CNN, and then all the rest is with either an SVM for the classification. The refinement is done with a linear regression. With the fast RCNN, as you see, you have much more steps that are taken over by CNNs. And finally, with the faster RCNN, it's actually also the region proposal that is not done anymore with the selective search, but already with convolutional neural network. And so in the following slides, we will see a bit more in detail what these three different type of frameworks mean and how they work. So let's look into region proposal based approaches. So we call them RPN, and here is a typical RCNN, the first one that I was mentioning. So I was saying they do their initial proposals with selective search segmentation with this typical objectiveness selective search that we mentioned before. Then they have what they have at the level 2 here, where they extract the region proposal, and they say that here they have roughly 2,000 of those. Then actually what they do is that they resize their region so that they have different batches with each time the same size in, that they pass through a CNN that classify, that gives them features, and they use them their features to perform a classification with an SVM. So instead of actually doing classification through the CNN, they just extract the features and then they use it for as input for both the linear regression refinement of the box and the classification of the object inside. So then fast RCNN is slightly different because in that case they do again their input image array proposal like before, but this time they do their they apply their convolutional network to the full image with the box inside. And so once they have their features extracted, they perform with a pooling layer, they extract the feature associated to the box that they want, meaning that actually instead of having to calculate all the feature each time for every single new box that they will resize, they have it already ready for the whole image, so it gains a bit of time. And afterwards, actually, they, as you see, once they have their pooled layer for their region of interest, they pass it through two fully convoluted layers, and they output both the classification and the regressor of the box, so that they can do at the same time the regression and the classification. And finally, faster RCNN, so where this time try to integrate the region proposal network in a CNN instead of having two different type of input with selective search on one side feeding afterwards towards the CNN. The problem indeed of doing a region proposal outside of the framework is that it's a disjoint training and that makes it very long. And actually, it's reasonable to think that we can probably learn what these proposals are. So the solution for that is to go slightly back to the proposition of sliding windows by creating very systematic box possibilities with different location, different ratios, different scale. So here we increase the variability of things that can happen with the different ratios and the scales. And we have a backbone, the CNN that is extracting the features, and those will be used to try to select with high recall the interesting boxes, interesting proposals. So that's why we call it a region proposal, because we want to use what we know of the different features to select the among all the box possibilities that we have systematically identified, all the possible regions that indeed can contain an object, and so to classify them afterwards. In terms of the architecture, most of the heavy CNN part is performed for the feature extraction at the level of the backbone, but afterwards it's usually a relatively shallow network that is used for the classification of the different proposals and for the regression of the correction to apply to the proposed boxes. Usually just one single fully connected layer. And then once you have your proposal, you go to a next step where you can continue processing over the boxes that you have selected or you have proposed to the initial network. So typically, things work like this. You have your feature extractor that is PGG, Inception, ResNet, whatever network you think is good for extracting features in your image. Then you go to your proposal generator, so your RPN, Region Proposal Network, that initially tell you, well, yes, this is possibly an object, this is not an object of interest, here is potentially a box regression that will make it better. And then so you have your proposal boxes that you are already selecting as yes, it's possible, no, it's unlikely. You crop from the different images. So you select them closely, and you go to the next step, which consists in really classifying the object in the box that you have selected. Is it really the object that you wanted to select? Which one of it is it? And also, if you need to further refine the box, how do you adjust the parameter for the box? So here we'll go a bit more in depth into what the anchor system for the region proposal network is. And here we define, just to remind you that it's defined on the feature map. And I focus a bit on this because you will have to try to implement it during the tutorial. So it's better if we go a bit in depth into it. And what happens here is that at the feature map level, for each available location, you propose multiple boxes that are characterized by the location, the scale, and the ratio. And classically, in 2D, for each possible center, you propose 3 scales and 3 ratios, so that give you 9 boxes. So for every single location at the level of the feature map in your image, you will get 9 anchors, 9 proposal boxes. You may actually try to choose a stride between the different anchors based on the image level, so that your change corresponds to the scale change between the image and the feature map. And the ratio is actually what allows you for a multi-scale approach, because as you see on the image on the right hand side, this is for a single location, and you have therefore boxes that are very extended and that have also quite different shapes in terms of the ratio between the height and the width. And so overall, you get as total number of anchors per image the number of your of the feature location that you have times the number in the height of the features in height, and times the number of scales times the number of ratios. So that in the end it's quite a big number. Here we'll go through an example of how to define anchors in a typical setting where we consider an original box of size 5 by 5, so height 5, width 5. We'll consider 3 different ratios, 0.5, 1 and 2, 3 different scales, 0.5, 1 and 2 again. And here are, on the left hand side, the equations that you end up with if you choose this for the different ratio and scale for the different boxes. So you define the center of your image based on the width and the height that you will have defined for that specific anchor type. And that helps you defining the corners of your box, top and bottom. So considering our example of 5 by 5 with the ratio and scales that I specified before, you end up with this list of possible heights and this list of possible widths. And here we consider a generic center at 2.2, and you need afterwards to use the different widths and heights that you will have predefined, and choose only integers because you don't want to have half voxels or half pixels considered in your anchors. And on the right hand side you have the pictures of what happens in the end with this when choosing this type of anchor definition choices for the boxes that you will propose in the end. So here again, it's simply going back to the anchors and trying to show you how to define them at the different location of your feature map. And here, just for illustration purposes, on the right hand side, so you may have other boxes overlapping much more than that. It's just here to show how they may occur. Here I'm just focusing a tiny bit more on the definition of the ground truth, because we talked before about the different objects that we need to detect, but we need also to understand how we get to see that one object is different from another, for instance. Here, considering connected components, so you have typical example of a matrix with a binary segmentation, and you end up with 3 different objects, one at the top, one at the middle left, and one at the bottom right, because they are not connected to one another. And one of the functions that allows you to do a connected component in Python is a function from the SciPy and image package, where you have the label function. And typically, to get a connected component, it depends on the structural elements that defines which type of neighbor you need to consider to form a connected component. So for instance, it's in situation where you have voxels that belong to objects that only touch on the corner, for instance, and you are just asking yourself if indeed you should consider them in the same element or as separate elements. But that's something that you can define and decide on using from the start. So once you have your objects, actually, one thing that is quite important is to try to be able to assign the different anchors that you have to the associated ground truth element. And because the problem is to know if a box is indeed a positive sample or not. And we need to know to which ground truth box it could correspond. So the idea here is to maximize the intersection of a union of the box that you propose compared to the ground truth box. And so here you have different from the anchor systems that we had before, the different IOU that you can get for the bounding box that is in blue, that is a ground truth one. And you have here the equations to calculate the IOU, what the overlap means, and you are actually able afterwards to choose based on specific thresholds that you will have predefined, either 0.5 or 0.7 of IOU, which of the ground truth, which of the anchor box correspond best to the ground truth box. And here it's typically an example of all possible boxes, or a lot of different boxes that were proposed, and finally just a few of them that are selected and assigned to the ground truth because their IOU is big enough. So classically, what you do to assign ground truth with anchors or proposed boxes, because there may be other systems that don't require anchors, we'll see that afterwards. You calculate the IOU between all the boxes that you have, or all the ones that are modified from regression, and all your ground truth boxes. Then you assign all the anchors that have for maximum IOU with ground truth lower than a specific threshold, you consider them as negative samples. all the anchors that have a maximum IOU with a ground truth that is more than a certain threshold, so that can be again modified, can propose 0.7 or 0.5, it depends, as positive samples, and you assign them to the ground truth box that has the higher IOU. Then you need to make sure that actually all the GT have been assigned. So you loop through all the ground truth and assign all the most overlapping boxes to it. So you may have more than one box, and you always do it in the limit of a minimum IU value, obviously. So let's see with an example how we do it. And you have in your tutorial a specific class that is called a max IU assigner, so you can look into that to understand a bit better how the assignment work. So every anchor box that verifies the IOU rule is considered a positive one. And if you have two anchors that are positive for ground truths, given ground truth A, well, then we assign both of them to this ground truth and we'll separate afterwards which one is best. If a ground truth box doesn't have any anchors, we just, because we don't have them yet, we just try to find another box that fulfills the criteria, and it's usually minimum 0.5. Otherwise, it means that we haven't managed to find a proper proposal for that ground truth, and that means that we will have issues in terms of recall. So overall, what happens is that for each anchor that we have proposed, we assign -1 if actually it's a negative proposal and we know it because it doesn't match with anything. Or we assign n, which is the index of the associated ground truth. And in addition of assigning which ground truth we consider, which ground truth box we consider, we also need to associate the label of classification to which it will be associated. And as we discussed before, you may have multiple objects of the same class in an image. So the ground truth box index will be unique, but the label isn't. So now what do we do once we have our proposals and once we have assigned them to ground truth? So we need first to select the best anchors, the ones that have a highest score, and we choose a specific number of them. We can apply some kind of refinement to them to try to make them better. And then we need to make sure that we don't use too many of the same boxes all the time. So we use what we call non-maximum suppression, meaning that when we have two proposed boxes for which the IOU between the boxes is more than a certain threshold, then we consider only for further use the one that has the highest overlap with the ground truth. And then for all the selected boxes, what usually happens is that we need to extract the features that correspond to those selected boxes. So we need usually to reshape the corresponding area feature map to a fixed object size so that we can apply the second stage, which is the RCNN head. And we can then classify or further refine the box. The things that we need to remember here is that the feature map may not be at the same scale of the image, and that we also very probably have non-integer value for the different coordinates. And if we need, we wouldn't be able to take just half a voxel here or half a voxel there to fit to the RCNN part. So we need to find solution to know which part of the boxes to take and how to deal with the non-integer value of the regress boxes. So when I was thinking of a box regression, and you will need to do it as well in your tutorial, it's a question of the delta that we are trying to regress in terms of the center, for instance, x and y, the width and the height, and this is typically what is used with the faster RCNN, or in terms of the relationship between the thing that you predict, the B thing that you predict, and the ground truth G. And you usually use smooth L1 there that is defined here for the loss to try to smooth a bit the way you regress your target for the box. And you can also use the a loss over the intersection of a union results between the box that you are predicting and the ground truth box. So now onto pooling and alignment, because of the problems of trying to map the coordinates of your anchor to the feature map scale, and to make sure that you actually really take in what you need. So in terms of mapping your coordinates of anchor to feature map scale, so for instance, imagine a VGG network. You begin with a 512 by 512 and you end up with a feature map that is at 16 times 16. So the original location of boxes maybe need to be divided by the scale factor, which is here 32. And you need naturally to take them at the integer value. So you need a quantization process in order to get the integer. First, you need this quantization at the level of the box definition, when you try to define where the border of the box will be in your feature map. And then you need to do it when you try to pull everything into a 3x3 array, like here. And so as you see here, you are losing the full bottom part of your scale when you are trying to quantize. So an alternative to it is to use array line, where actually you don't do any quantization, but you actually cut directly by your grid into the 3x3 that you want to obtain, and you apply some bilinear interpolation in order to combine the different picture values of your feature map in this 3x3 shape. So now that we have done our proposal, that we have extracted the feature that we need to use through the array pool, array line, we go to the second stage of the network, which is the refinement and the classification, the final classification. So classically, the RCNN head, it's two shared fully connected layers, and then followed by two branches that are separated, where the classification branch is just a fully connected layer, the regression branch just a fully connected layer. Obviously, you can make all the variations on architecture that you want to do, either sharing or not the weight, either doing convolution instead of fully connected layer, changing the choice of the loss for the box refinement. And you can also obviously change your classification loss if you need to, and usually it's among many classes, and typically you use a cross entropy there. So let's recap. Usually what happens at first, you need your backbone. So your feature extractor, your big CNN. That's the first step. Then once you have your features, you are trying to extract the boxes that are of interest to you. So you have all your anchors, you have all the associated boxes, and your RPN. The purpose of the RPN is for you to classify each of the anchors as saying, yes, it's supposed to be a probable box that I may be interested in or not. And from that selection, saying afterwards, well, now that I have the boxes that I need, I first extract those boxes, I perform the RI pooling or RI line, and I feed the selected proposals to a network that classifies them and refines the boxes. Now that we have seen what RCNN, fast RCNN, faster RCNN are, we will go into some other variations that are interesting of the same concept of the two-stage detector. And the first one that we'll look into is grid RCNN. So in that stage, the main difference between grid RCNN and the previous one that I presented is what happens at the level of the box refinement at the second stage. So everything up to the RPN module selection of boxes is the same, but afterwards things are slightly different because instead of regressing out the boxes components such as the width or the height, here what's happening is that we are regressing a heat map of the grid around which the borders of the box are. So that's why it's called grid RCNN. Another extension of the faster RCNN is mask RCNN. So I talked about it briefly before, and that improvement is actually simply trying to move from the object detection and localization part to go to an instant segmentation on top of everything. So what happens is that in addition to the branches of classification and box refinement, you have another part that is actually mask branch that performs the segmentation based on the boxes that are provided. So it's performed on the realigned box, and it's only learned if the classification of the box is not background. And so on the bottom, you see an example of the results with both the boxes, the classifications that are associated to, and the instant segmentation in different cases of daily life images. The third slight variation around the same idea of multi-stage detection and classification is a multi-level proposal, which is called Cascade RCNN, and it comes from the observation that actually the quality of the detector, which is what your RPN is doing, is highly dependent on the threshold you are putting on the intersection of a union that defines if a box is negative or positive, or if it should actually be associated to a ground truth. And if you consider only higher IOU, you have less samples, and if you have lower IOU, you have lower quality of the proposals. However, if you have less samples, you may have issues of recall that may become very low if you don't manage to appropriately classify them afterwards. So what they observed is that actually the IOU is usually higher after the regression of the boxes. Obviously, after you refine them, it's supposed to be closer to the ground truth box. And so what they are doing is they are performing their RCNN at multiple levels. So they are first doing a first proposal in which they classify as belonging to a class or not. Then they apply their ROI line, and then progressively they refine and make thresholds over the RU be increasingly higher in order to be selected for the RCNN part. And that in their case improves significantly the performance. Before we move on to summarize a bit all what we have seen and we go to try to see what happens with one-stage object detection framework, I would like to mention and go a bit more in depth with what happens when you need to look at your image at multiple scales and a specific type of way of actually dealing with this multi-scales problem, which is a feature pyramid network. So for different objects, you may have an object at different scales on your image. For instance, if you consider a car that is just in front at the first stage of the image, and another one that is much more in the distance, you would have that due to the perspective at different scales. And people have imagined multiple ways of dealing with that. So we have seen earlier the question of just getting the image at different scales, so putting indeed the image at normal scales, then downsampling by 2 and further by 2 and further by 2, for instance. And in that case, it's what you have as a featurized image pyramid, where for each of the scale of the image that you consider, you create specific features on which you predict your boxes and location of your objects. Another way of actually dealing with multiple scales is actually just to consider a single feature map by downsampling progressively your image and predicting only at the last level of downsampling, which is a single feature map. Another possibility is actually to say, well, I consider my initial image and I will progressively extract features at different scales and predict from each of these feature maps specific boxes that I can extract there. But in that case, you cannot get any information from the features that you extract afterwards. So it's only one step at a time. And that's what we call the pyramidal feature hierarchy. And the feature pyramid network is actually when you go from the image and you create different feature maps from this image at different scales, but actually you only perform the prediction when going back on the U of the tree, progressively predicting back by using what is available from the features up. And so you have on the side bottom right exactly what happens in terms of the upsampling stage and the combination with the feature map previously extracted. So you saw before in all these two-stage network, you have multiple building blocks. So we mentioned before the need for a backbone for the RPN array extractor with array pool or array line. The need for the second stage with the RCNN that has either shared or not weights between the different tasks, convolutional architecture or fully connected layers, and where you may change the way you define the target and in terms of the location of the box. You just saw the question of using feature pyramidal network to help with that, cascaded RCNN or instant segmentation with, for instance, mask RCNN. And we saw different and a large number of parameters that could impact greatly both the results and the training process. So the definition of the anchors in terms of the size, the ratio, the scales that you use, the definition of what you assign, and the thresholds that you use for the IUU, for instance, in terms of deciding what is a positive sample. the number of samples with a positive versus negative ratio, in particular for at the RPN level, when you are trying to define if an instance is indeed a positive sample as defined by your association with the ground truth. You may want also to do some padding prior to the extraction of the boxes. You may want to use non-maximum suppression, and so you have a parameter here in terms of to what degree do you consider that the boxes are overlapping. In terms of the number of proposals that you will finally feed into your CNN, and the imbalance strategies that you choose in terms of negative versus positive samples in your trainings. So, one of the important things in region proposals and object detection, and we'll come back to that problem quite often, is the problem of imbalance between your negative and your positive samples. And classically in the RPN, because you have many anchors, when you try to train your classifier of anchors saying, well, this anchor is positive, this anchor is negative, because it's what the RPN is trying to do, you will only use a fraction of the negative boxes, and usually you take a ratio of 3:1 between the negative and the positive samples. To choose the negative samples, you have different ways. You may actually want to do some hard negative mining, meaning that you really want to separate well between the negative and the positive, and you take the most negative proposals in your set of anchors. You have obviously ways, and we'll see that later, of skipping the RPN part, the region proposal network part, and try to get directly from the anchors to the final prediction. So that's typically what RetinaNet is doing with the focal loss, and by maximizing a specific ratio between positive and negative in the SSD network. And for that, again, the SSD solution is to choose negatives that are the most negatives. So now we will go into, we have covered mostly all the two-stage detector, and we'll go into the single stage detector, one-stage detector, and this is one of the first one called single shot detector, SSD. And in this instance, what happens is that actually they use again dense anchors, so the same system of anchors at multiple locations, but they do it at multiple scales. And they use for, instead of having to choose via an RPN before doing the RCNN, they choose a strategy of hard negative mining, where they decide to train only on a specific ratio of negative versus positive samples, and choosing especially negative samples to learn properly the difference, and they do a regression over the box in order to refine it. And below you have actually a copy of the network that they're using for it. The next interesting one-stage detector is what's called RetinaNet. The general architecture is actually a feature pyramidal network where they extract all their features, and then at each level they slowly go back to get actually input from the previous level and get their feature at each level of the pyramid. They choose a very narrow range of in between, meaning the ones that they consider negative versus the ones that they consider positive, but they don't share the weight there between the location and the classification network. What they do though is that they use what's called the focal loss, especially to deal with the imbalance between the negative cases that are always many in an image and the positive samples. And what you have here is how they calculate this focal loss. And the important aspect here is that it looks a lot like a cross entropy loss, but actually with these gamma parameters, it allows them to downweight the easy example. And so that's what you see with the graph on the right-hand side up, where according to gamma, actually, it shows that if the probability of the ground truth class is very low, then the error is much stronger. But actually, as soon as they arrive close to 0.5, they stop costing it too much. So all those were one-shot detector, but they are still all anchor-based. So we saw in the multi-stage approach that you have sparse proposal over your image, and that enables you to easily do some pruning over the negative samples, and then you need to do your refinement and the classification of the proposal, with the risk, obviously, that if your first stage is not working properly, you may have a low recall in terms of the proposals. And we saw a lot of different variation on how to provide the proposals, how to perform the refinement, and how we progressively integrated the different region proposal system within the full framework, so that it became an overall training system. I'm just here contrasting with the original RCNN that was simply using this objective selective search in order to create the proposals. In contrast, you have anchor-based one-stage approach, where actually here you have dense proposals, and your main issue there is to deal with the imbalance between the positive and the negative proposals. It's often faster, but it tends to be slightly less accurate. And it's especially in this type of systems that we saw the use of the feature pyramidal network. So now we have looked a bit at what does it means to be either one-stage or two-stage network in terms of object detection framework, and we have mostly focused on anchor-based system, but we'll see that there are also other solutions that are anchor-free, and the rest of the lecture will focus on some of the examples of these anchor-free solutions. So anchor-based means that you have a definition of preset boxes that are usually regularly spaced, and you have them from the start of the optimization. We saw that in the one-stage ones that needed to be densely defined, and in the two-stage one, what happens is that these densely defined anchors are actually prone to the region proposal stage. And we saw as well that you could apply them at multiple feature levels. It's in particular what was done with the SSD. It has high coverage. It's accurate from the starting point, but it's usually quite memory intensive, and it's very, actually when you think of it, it's quite difficult to transform for the 3D version. And it's quite complicated to implement. You will try to do so in the tutorial. You will see how things can quickly get a bit complicated. It's also dependent on a large number of hyperparameters, especially regarding to the definition of the anchors and the imbalance training. In contrast, the anchor-free methods need some other definition for the object detection. They are often actually using not the center, the height and width, but also corner-based or key point-based, center-based sometimes. So you have a large variety of ways of actually defining boxes in those solutions. They're usually relatively easy to implement, but you have the potential for ambiguities, especially if you have overlapping objects. And they tend to suffer a lot more from high data imbalance, so they are really sensitive to the training setup. And one of the most well-known one is YOLO, and YOLO stands for you look only once. So there are some you can easily see what happens on some YouTube links that were made to in terms of the application of YOLO. But what happens in a specific instance? So what they have is that they have an image that they divide in a grid of S by S cells, and they decide for each grid cell to predict a certain number B of boxes. For each box, they say that they define X, Y, W, H, and the class that things correspond to. So the XY is the distance of the center of the bounding box to the center of the grid cell. And the width and the height are always given with respect to the full image. And they say the confidence for a predicted object. That is a conditional probability given that there is an object. The thing is that even though they propose multiple boxes per image, they only set one set of probability per grid cell, so it can only be associated to one class. And they have a loss function that is decomposed as shown on the right-hand side. So they have first a loss function regarding to the coordinates of the box, in case there is an object that is in that cell. They have a loss function over the confidence that there is an object in that specific cell. They have loss over the probability of belonging to a specific class, and they then make a weighted sum of all these different losses. So what they observed in this specific instance is that they had only 2 boxes per grid cell. So they had, because of this relatively small number, which means that they can at most propose 2 times S squared object in the image, that they had a relatively low recall, and they had problems with overlapping objects and problems with tiny objects, especially if you imagine that you have an object that is much, much smaller than the cell it's in. So what the solution was for that was to consider more boxes per grid cell and more than one class per grid cell. So, for instance, in case you have a head and a tail, that could be typically an example of things that you could have within a cell, but they would belong to different classes. So they went slightly back to the questions or to the possibility of using anchors, but instead of using a predefined size anchor, they really handpicked the dimensions that the anchors should have based on the features of their objects and the ground truth that they had. So then they were trying to find cluster of box sizes from the ground truth in order to define what were the appropriate anchors and anchor size that they should choose. That means obviously that the training that you do is only applicable to similar type of images with relatively similar objects. They also made sure that the shift was within the cell, so they had a logistic activation function in order to bound it between 0 and 1 in order to avoid the box to wander around. And they increased as well the box scale, so they tried to learn at multiple scales by actually, instead of using a feature, a pyramidal network that like we saw before, they decided to present the image at different sizes. So every few iterations, they were downsizing or zooming in with the image in order to present it in a different manner and see objects at different scales. And in order to further improve on the final classification, they put together hierarchical conditional probability for learning classes, meaning that they had a tree of the different categories. Now that we have seen YOLO, I just would like to mention another type of framework, which is again anchor-free, again a one-stage detector, and it's CornerNet. So CornerNet actually tries to identify the two opposite corners of an image, of an object in an image, and to do so, they use a network that is actually very similar to UNet. It's called the Hourglass network, but again, taking the image at different scales and resolution and going back to the same resolution. And the main difference is that they don't have this this connection, the horizontal connection that you have with a UNet. So what they do there is that they try to get heat maps for the top left corners and for the bottom right corner of each class. They try then to have what they call embedding, which is actually the fact of belonging to the same object or not, so that they can group together top left and the bottom right corner of the right object. And they perform their grouping of corresponding corner with definition of a slight offset in case they have multiple scales of the image and they need to again play around the fact that when dividing they may get non-integer values for their voxel position. So what they do for their corners, for their encoding of corners, they actually, instead of trying to define just the corner, just a unique point, they first have decreasing Gaussian to try to cost more the error in detecting the corner if they are far from it, but if you are still in a relatively reasonable radius, they still consider it. And they have this two-stage corner pooling, where they look at both the horizontal maximum and the vertical maximum that then they propagate along, and when they sum the two maps of their pooling, they get the location of their corner at the maximum of the two. So here it would be the number 10. And so I was telling you before about the embedding system, and so that's what the lpush and lpull loss functions are doing. So what happens when they are training the embedding is that they consider that ETK is the value of the embedding for the top, EBK is the value of the embedding for the object K bottom, and they have EK, which is the average of the two. And they want that actually these two are as close together as possible because they need to belong to the same object. So that's what the pool is doing, meaning that when it's within the same object, it needs to pool together the value of the embedding. While the lpush does the opposite, meaning that when you have two different objects, the embedding value must to be as far apart as possible, which is what's done by the push loss, which is pushing apart the embeddings coming from two different objects. Their LDET, loss determination, is detection is actually the one that is quite close to the focal loss and is actually trying to make sure that they detect correctly the object, again dealing with the imbalance. And while the L-off is actually an offset that is related, as I was telling you before, to the fact that the detection may be done at a different scale than the original image, and so that they need, if they were to only use the integer value, the offset would cause issue. So they are making this smooth L1 in order to deal with the problem of scale changing and associated quantization. And the final loss is, as usual, a weighted sum of the different component losses. So now into another anchor-free system, which is this one, a one-shot system, which is actually slightly different in terms of how they consider what an object is, because here what they do is they try to consider object at different scales, but every single point within the box for an object is actually counting and helping them define the final bounding box. So all foreground points have regression targets. And the object bounding box, they are only defined onto a specific feature map, meaning that you wouldn't learn an object bounding box if it doesn't correspond to the scale from a feature map that doesn't correspond to the scale of the object. So naturally, if you are close to the border of the box, you are much more likely to make some mistakes because you may not have all the context that allows you to do to find the borders of the box. So they have a loss over the measure of centerness of the point that is deciding, and so that it's used to downweight the average of the bounding boxes. So instead of just simply averaging all the bounding boxes that they regress out for foreground points, they actually make a weighted average based on how far it is from the center of the object. Another interesting solution that also looks at defining the object at different feature scales. So we saw that SSD was doing it, that FCOS was doing it, that to some degree YOLO v2 had a similar aspect, and that's most of the solution were actually quite related to the feature pyramidal network. Or similar, here we have Foveria box, which tries to do the best of RetinaNet and an FPN, and for that each feature map will actually predict object within a specific scale range. So they define empirically what that scale range should be at each feature map level, and they define a fovea of an object for the positive standard sample. So compared to what we have with FCOS, where actually everything in the object can contribute to the final detection, here it's only from the fovea of the object, so from the center of the object, that you can predict the box that you can average afterwards. And so they define at each level, and for only the object within that feature map scale level, the different targets of their points. Here they were considering opposite corner points for the boxes that you then define at the scale level. It's what is on the top right. But the positive points that are used for the definition of the final box are only the one defined by this x second and y second at the Foveria box at the scale level. And it's only from these positive samples within the Foveria that the final coordinates are defined. So we arrive roughly at the end of this cataloging of all the possible solution of one-stage detector. and the comparison with the two-stage detector. So you have here some kind of summary of the different characteristics. So if they're end-to-end or not, if they're using anchors or not, the number of stages in which they work, what is the type of backbone for extracting the features, if they're using a feature pyramidal network or not, or if they could or not. What type of architecture do they propose if they have a region proposal? What type of region of interest extraction do they use if they have one? So that's mostly or only for the two-stage detectors. If they care for imbalance in some way, or if they have specific things implemented there, H&M stands for hard negative mining. If they share their weight between their regression and the classification part, if the RCNN architecture, they have, what it is, and finally, what type of target do they regress? If they regress the center, width and height, only the corners, the distance to the borders, or the corners location, and what type of loss they use for their regression and for the classification. So before we go a bit more into less computer vision example and a bit more on how these things have been used for medical imaging and if other solutions have been implemented for 3D problems, just wanted to mention the type of performance assessment that you may want to do, because if you want to compare different methods, different models, you may want to find a way to properly evaluate them. So I just put definition of recall and precision here, and the typical evaluation framework that is used in the computer vision world datasets and computer vision world evaluation system. So for instance, with average precision and average recall. So usually when you consider you say AP 75, that's average precision for the positive IOU of above 75. So you get your precision for all your different images, only considering a positive sample if the IOU is more than 0.75. And when you consider, you talk about AP, it's the average that you get when you calculate AP at different IOU thresholds from 0.5 to 0.95, for instance, by a step of 0.05. That's typically what's done within the COCO dataset, which is one of the most well-known datasets in terms of object detection, object localization, and classification. That's common object in context. You have also ImageNet, World3, PascalVox, that datasets that are often used for the evaluation of object detection. And on the right-hand side, you have just a summary of the performance of what happened for the different models that we talked about here today, and where you have the average precision, and then the average precision at 50, at 75, and then only for small objects, medium objects, and large objects. So now, let's try to see a bit more what's happening in the medical imaging world in terms of object detection. So there has been a few direct adaptation of the works that I've mentioned before, especially when they were used in directly in 2D images or using only slices. So there is some with lung nodule detection. They're using mask RCNN or single shot detector, YOLO and faster RCNN used for mammography, mask RCNN for instant segmentation of tear of the knee meniscus, mask RCNN also for nuclei segmentation in cell segmentation. Some of them are also being modified slightly, such as retina UNET, and a 3D version of the faster RCNN for small brain lesions, for instance. So here just some pictures actually taken from these publications, where you see application to mammography on top with either benign and malignant lesions with the associated bounding box, the knee meniscus tear detection and segmentation with mass CNN here, and for nuclear cell segmentation. So here I actually put that picture from the retina unit paper that was done for lung nodule detection, comparing when using FPN, the mask RCNN, faster RCNN, and RetinaNet. And they actually transformed it to use some kind of a UNet U feature pyramidal network with faster RCNN, and then their detection unit, where actually at pixel level they get their connected component. And the interesting thing to mention in this specific instance is some kind of a strong improvement to the non-maximum suppression. I told you that we were often using it in order to eliminate boxes that were too close one from the other. So if you have two proposals that are really, really overlapping, you wouldn't, and they are exactly the same scale and so on, it's very unlikely that it's two objects, and it's more likely to be the same object, but where the proposal is just slightly shifted between the two. And what they use here, instead of doing this pruning there, is that they use test time augmentation, so running multiple instance, non-probabilistic instances at test, in order to get a number of boxes at one location. So they get multiple instances of the same solution, and you will see that it's sometimes used also for uncertainty, but that's to be seen in the uncertainty lecture, and that allows them to have overlapping. They do that by having overlapping patches and not starting from the same point of view when they do their test time inference. And what they do afterwards is that they cluster the different boxes together, and they somehow try to overlap them with a specific cluster weight, where it allows them to say to which cluster they belong and to weight the different average coordinates. But that was all done in 2D. In 3D, the main issue is that you cannot really transport easily the anchor system because it's way too memory intensive. And also because for the backbone, doing just a segmentation task wouldn't work, so you need something else. And also because when you think of it, while in 2D it's reasonable to think of boxes as aligned to the different axes, in 3D that becomes much more complicated and much less true, and you may actually lose quite a lot of space and of precision if you were only to consider axis-oriented boxes. So that's where actually thinking of other type of boxes, or maybe not boxes, but other geometric objects can be interesting. So here it's an example of trying to segment or trying to detect enlarged perivascular spaces. The backbone was actually trained by, instead of running directly a segmentation network, by running a regression network that was actually trying to regress the distance to these different elements that are actually very small and very sparse in the brain. then a classical region proposal network. And instead of trying to realign everything to the same space and trying to do batches like this, it was just doing a for loop over each box through the network in order to classify it. But instead of using a box here, we're using an ellipsoid. So that finishes the lecture on object detection. And just to summarize, if everything has been properly understood and properly covered, by now you should know the difference between one-stage and two-stage detection frameworks. Know the difference between what anchor-based and anchor-free detection frameworks is. Know different strategies that can be used to limit the imbalance between positive and negative samples in the context of object detection. Understand the feature pyramidal network. Know and understand the difference between box extraction schemes and what they are doing, and know a few examples and details on object detection methods, and have a bit of a feeling or an understanding of the different challenges that you may encounter in object detection and specific uses in medical imaging. Thank you very much for your attention.